All right, hello class. My name is Devin Lang, and this is my presentation on our linear regression project that we've been doing throughout the course here. And for me, I chose to look at variables in Major League Baseball, and I wanted to look at player salaries and see if there was a correlation uh, from those salaries to on-base percentage. And on-base percentage in baseball is how many times the percentage that players are reaching on base, no matter what, however that is. So that could be a hit, that could be a walk, that could be a hit by pitch, that could be a home run. However they reach base, this is calculated into that based off of how many at bats they have. And uh, so on base percentage in baseball is probably the most important stat in the game. Um, the more that players are reaching base means more likely that teams are scoring, and the more that you're scoring, the more that you're winning. So I wanted to see if there was a correlation between player salaries and their on-base percentages. So if a player had a higher salary, does that mean that they have a higher on-base percentage? And if they have a lower salary, does that mean they have a low on-base percentage? So I took a sample from a data set that was part of one of the websites that was provided for us that had data sets on them. I found one that was player statistics from the mid 90s in Major League Baseball and used that sample. It was a wide sample. It was over over 400 players, but I noticed that um, I weeded it out a little bit because there were pitchers, because pitchers do sometimes hit in baseball, but they don't hit a lot. So their statistics and statistics of other players that just don't bat as much could have skewed the data quite a bit. So I wanted to make sure I went through and removed those pitchers and those players that didn't bat that often. I mean, there was players in there that had like 10 at bats, so they had like an on base percentage of like 90%. It would have just skewed the data and not helped what I was looking for here. So I removed those, and then I think I weeded it down to about 150 players, and then I took a 50 player sample from that, a 52 player sample from that. So I got inspired for this from the movie Moneyball. If anybody's ever seen it, Brad Pitt plays Billy Bean, the Oakland Athletics general manager and former player for the team. Um, and what they do in the movie is this is when statistics really started to kick into effect and more teams started to look at statistics in baseball. The Oakland Athletics at the time were a lower salary team. They weren't like the New York Yankees that had a lot of funding. And so Billy was tasked with rebuilding the roster after a very successful season where they almost won the World Series, and then they lost a lot of their key players to these bigger teams that had a lot more money. Um, so Billy was tasked with building a team with a lot lower salary, and he ended up getting together with a statistics genius where they started looking at certain statistics to build a team with players that were not known but had exceptional statistics in certain areas, but just were getting overlooked because they weren't good in other areas. So that's where I kind of got the inspiration for this project from. And when I seen the data set on the website, I was like, oh yeah, I'm definitely going to do this because I love baseball, I love sports. So going into our statistical analysis here, first we have the two histograms, one for salary and one for on base percentage. This is to get um, a, a visual for the frequency of each salary and each on base percentage variable where they lie. So on the left here, we have the histogram for the player salaries. And you can see on this histogram that it's skewed heavily to the left. Um, you have the majority of the players, especially with it not being modern time, you know, salaries, and this is back in the mid 90s, so a lot of players made less than $1 million. So even with the players that I did remove, I mean, a lot of them were making under $1 million. There was not a lot of players that were making more than three, which you can see here on the histogram. There's a few, there's 4 or 5 that are over $3 million. Other than that, every other player is underneath that, and that's why we get a skewness heavily to the left for the player salaries. Now, if we look over at the on-base percentage histogram, you can see a very normal distribution with a bell shape, um, where you get the apex of it, that bell, at about a 0.30 on-base percentage. So this is a very evenly distributed variable, and um, you, there's probably not going to be any outliers with this from what we see on this histogram. Whereas on the histogram for salaries, we're like, there's probably going to be some kind of outlier, whether that be the top amounts or the amounts that are very, very much lower. So moving forward, we're going to look at the box plots now for on-base percentage on the left and the box plot for salary on the right. Now, uh, like I said in the histogram, you can see this is a very normal distributed uh, data set for the on-base percentage, and you can see that there are no outliers that lie above or below for the box plot there. But when we move over to salaries, we do have an outlier, um, and you can see that that data sits very low on the box plot because, like I said, a lot of those player salaries are under that 2 million, more, the majority of them under a million. So that's why you're seeing that box plot data set so low on the box plot. And then you see you have a star all the way at the top there at about 6.1 million. That is Bobby Bonilla. He was making a ton of money for the Mets back then, but well deserved because he was a big home run hitter. So his salary is the outlier here. He's the only person that was over $4 million in salary. It was insane. Not players nowadays are getting paid way more, but um, the main thing that we want to see moving forward is there a correlation between these two variables? If, for instance, that outlier of 6 million, if he's getting paid $6 million, does that mean he has a higher on-base percentage than everybody else that is within the sample? So continuing on, we're moving into the correlation and regression analysis. And as we can see, when we put both variables on a fitted line plot, the data points are all over the place. And it, you can see with where the where the fitted line is, it's not looking good to see a correlation. So for these two data sets, um, the correlation coefficient is R equals 0.281, and the p-value is 0.044. So already we're getting some red flags that it's not going to be looking good here. And then when we look at the regression line equation that we got from our Minitab analysis, uh, the regression line equation is salary equals negative 1,306,146 plus 8,141,790 times the on-base percentage. So those are some wild numbers to come up with. And now looking at the R squared variable here, it comes in R squared is equal to 7.9%. So R squared is showing how much of the salary variable can be explained by the on-base percentage variable. So how often is one variable affecting the other? and it's only 7.9% of the time. Um, on the fitted line plot, you can see a lot of, it's not where the line is, there's not a lot of data points right on that line, which is what you want to see if there's a correlation. You got some that are just way out at the top of the graph, and then you got a lot of the data that is below the line. And you can see also from this fitted line plot that just because a player, like you could see at the top of the graph there, that 6 million salary, and his on base percentage is slightly below 0.40, and you got one other player there that's getting paid a little bit over 5 million, and his on base percentage is slightly above 0.40. But if you go down on the fitted line plot, you can see there's multiple players that are getting paid less than 1 million there, that are hitting above, getting on base more frequent than those two that are getting paid millions more than them. And you can see that with a lot of the salary, just because they're getting paid a lot less does not mean that they're not performing as well as the players that are getting paid a lot more. So after running all the tests and looking at all the data and everything, we can conclude that there is no correlation between the player salary and the player on base percentage. So since there's no correlation between the two variables, we can conclude that higher paid players do not necessarily have a higher on base percentage than players that are getting paid lower. Um, as we've seen on that fitted line plot, there was players that were getting paid way substantially less than players at 6 million that were getting on base better than them. So lower paid players are just as likely to perform as well as higher paid players. I thought maybe there was some kind of correlation with getting paid more, that you would be getting on base more, that you'd be performing in that statistic better than players that are getting paid less. And there was a reason why those players were getting paid less, but that is not necessarily the case here. So like using MLB general managers could use this kind of statistical analysis that we've done here to maybe justifying how much they're paying a player when it comes to contract talks, or they could use this data to go out and find cheaper players that can fit into their team and perform in a certain way, whether that's on base percentage or a different variable in baseball, home runs, slugging percentage, things like that. They can use this for any statistic in baseball. I could have chose any statistic. There was multiple statistics that were available within the data that was presented, but I wanted to look at on base percentage since I knew that it was the most important stat in baseball. So here's my references. That is the website where I got the data sample. And then there's a couple of references there where I got some information. So thanks for watching, and you guys have a good rest of your semester.